In this lecture series, we will try to understand the chemistry of pH at the molecular level. pH is a very important concept in chemistry and biology, and it is the most neglected topic in academia. pH simply means the power of hydrogen ions, and it is governed by the laws of thermodynamics. So here, we will try to understand the key concepts associated with the pH in a more intuitive way. Before going to the pH and the effect of acid and base, first we should learn how water behaves. Because our pH scale is defined for water-based systems only. So, let's look into the water. As we all know, water is made up of 2 hydrogens and 1 oxygen, and it has a molecular weight of 18.015 grams per mole. That means, if we take 6.023 into 10 to the power 23 number of water molecules and take their weight, we will get 18.015 grams. Assume that I have 1 liter of pure water. That means it contains a large number of H₃O molecules. Here, the number is important because the entire concept of pH is based on this number. Therefore, let's quantify the number of water molecules in 1 liter of water. While doing so, we will assume that the density of water is 1 gram per ml. If we have 1 liter of water, then its weight will be 1000 grams. Since molecular weight of water is 18.015 grams, 1 liter of water contains 55.5 moles of water molecules. So in 1 liter of pure water, we have 55.5 moles of water molecules. Therefore, the concentration of pure water is number of moles of water molecules divided by volume of water, which will be 55.5 molar. This number is very important, and it is a huge number. If we convert it into the number of water molecules, then we have 334.33 into 10 to the power 23 number of water molecules. But not all water molecules present as H₃O in bulk water, because of temperature, polarity, and free energy, intermolecular proton transfer takes place between the water molecules. It is purely governed by the laws of thermodynamics. This is called autoionization of water. So at any given time, if we have 1 liter of water, we have few molecules of H₃O+ and equal number of OH- ions. And a thermodynamic equilibrium is always maintained. We will discuss these equations later in our other lecture series. But for now, it is sufficient to know that if we have 1 liter of pure water, then we have 55.5 moles of water molecules, and among which few exist as H₃O+ and OH-, and their concentration is governed by thermodynamics. It is well evident that at a given temperature the concentration of these ions are fixed. For example, at 25 degrees Celsius, we will have 10 to the power -7 molar of H₃O+ and 10 to the power -7 molar of OH- ions. This number seems to be very small. But it is not the case. Let's quantify it. So in total we have 334.33 into 10 to the power 23 number of molecules. Among them, 10 to the power -7 molar of H₃O+ and 10 to the power -7 molar of OH- ions are there. That means in 1 liter, we have 6.023 into 10 to the power 23 multiplied by 10 to the power -7, which will give 6.023 into 10 to the power 16 number of H₃O+ and same amount of OH- ions. Again, if you look, this number is not a small number. We will see how the number gets affected when we add any acids or bases. As we discussed, there is a thermodynamic equilibrium exists between the water molecules and their ions at a given temperature. The equilibrium is represented by this. We know at given temperature, let's say at 25 degrees Celsius, we have a fixed concentration of these ions. This can be estimated by measuring the conductivity of pure water. This is 10 to the power minus 7 molar of H₃O plus and 10 to the power minus 7 molar of OH minus. So remaining 55.5 minus 2 into 10 to the power minus 7 molar is the concentration of pure H₂O. So, the equilibrium constant becomes this. Here, we can write 55.5 minus 2 into 10 to the power minus 7 to be nearly equal to 55.5 because there will be a very small difference between them. Therefore, this number is a constant. If we multiply with the equilibrium constant, then we will have a product of H₃O plus and OH minus concentration, which is called ionic product of water. Since at 25 degrees Celsius, the H₃O plus and OH minus concentration is 10 to the power minus 7 molar, this is the ionic product of water, which is 10 to the power minus 14. If we change the temperature, it impacts the molecular energy, so more or less dissociation may be followed. For example, when the temperature is reduced to freezing temperature, the auto-dissociation decreases. And the new concentration of H₃O plus and OH minus are 10 to the power minus 7.5. So, the ionic product will be 10 to the power minus 15. Similarly, at 60 degrees Celsius, the concentration becomes 10 to the power minus 6.5 and the ionic product will be 10 to the power minus 13. So it explains at a given temperature how many water molecules are dissociated in 1 liter of water.